have a new clock. You see that?
Oh,
Oh.
Oh.
a few too many faculty meetings ran over, huh?
Yeah, I just replaced it.
Oh, you did?
I did. Nobody want today, so I did.
Yeah.
I just want to have a clock here and easily to see that.
I mean, it's definitely not a university supplied clock. It's got a little style. It's too nice. It's too nice. It's too nice of a
It's
clock for
cheaper.
it to come from the university.
I mean, just have a time there. Okay. And then just on time. 1 minute.
Time isn't relative.
Time minutes. Yeah, we need wait another.
Follow them right on the letting me see it.
I just remind the end of our class, last class, we discussed the behavior of this, we introduced a new phase factor, right, that shift. So what this means physically. Okay. Now, this is for the potential wheel. We have, let me see now. And this is energy positivity. So let's compare. Free particle. Then we know what happens. So for free particle, when R go to infinite, we also have a spherical, in the spherical coordinates, right? We have a spherical function, or spherical wave function, which is like this, which is R L, also K E R, and R go to infinite is K E R sine K E R minus L pi over 2. So then you can see they are almost the same. The only difference is here. Is this term, right? So if you look the behavior of this spherical wave are the same, just a phase shift. So what means, so this is a described scattering because you see we have energy positive. So particle from infinite come to here, and then when they go to this, if this is A, and interact by this, or even by this potential well. So this the wave function perturbate, right? And so then go back, right? So then what happened is, like here we have a, from infinite it's like free particle, right? So we have a particle here with initial energy, which is initial kinetic energy term, right? And also this initial angular momentum. Then the particle have just use K in, like equal to, in our case, Ke, if you remember, we introduced Ke is out of this A, right? Out of this direction. Then suppose we have here, we have a target here, and we have a potential zone, which is A here. So then the particle will come to here. It will influence, I was scattered by this because this is a potential. It will go to, okay, go to this direction, right? So we know that in this area, when R smaller than A, we have the region, the solution is this one, which is a spherical Bezier function, right? Something like this, if you remember, which is a KIR. But then when after, because in this area they influence or interact with this potential here, so this plane wave will perturbed or influenced by this, then they will change, and they keep going, right? Keep going by scattered certain direction. So when they keep going to here, that is spherical function here, but compared with a free particle, it is determined by this. So you can see what happened is this one is this scattering effect of or total effect, include all total effect of the scattering due to this potential, right? Let's use R here, even though we know R in this case, simplified is just a constant when R distant within the area. So within this zone here, you have the effect by this, and then the effect that finally actually is just nothing but a shift. So this shift, how much it shift, it really depends on the initial effect. Now I'm going to write down here, initial energy or initial kinetic energy, and also initial angular momentum. I think you all learned this theoretical mechanics, right? Chapter 3. Yes, you have a question?
Yeah, so whenever you have the arrow that says from R going to infinity,
Uh-huh.
how do you get from R2 to the next line down?
This one, right?
Yeah, going
Yeah.
to the next line down. Can you
Yeah.
walk through that again?
Yeah, from here to here, right? Yeah. So that R2 with any R is this function, right? So when R2 go to infinite, this function will reduce to here with this. I think last class we discussed, right? Combined with this. So that is this is spherical wave function here. This doesn't matter. This is just constant. So that is behavior R2 since this is region 1, right? This is region 2.
Yeah.
So we have a region 1 just within here, and when R go to infinite, only R2, right? So only consider R2 behavior, and then when the R go to infinite, it's behavior like this function, and that's characterized by this. So we want to see, okay, so this what looks like that when we go to infinite, the behavior or the wave function of this is just like this spherical wave, and then if you go far from this one, it's like free particle. But this free particle has already been influenced, affected by this when during the path from here to here, right? If without this one, this free particle just goes through, and if you use the spherical wave to represent the plane wave, is this one, right? So that is difference, and this difference reflect this, or this include all this difference, and this difference is due to this scattering effect of the potential. That make sense? Okay. All right, so this is the topic for the spherical potential wave. Now we go to another topic is isotropic harmonic oscillator. This type is, if it's isotropic means no orientation dependent, right? Like spherical symmetry. So the potential, that's first, potential is only R dependent, right? And here, R, no boundary. Right, so the R from 0 to all the infinite, the potential is extended in the whole space. So that is behavior not like this. This by, if you remember, this potential just defined R small a and 0 R is for giving range. So we have a boundary at this one. But here there's no boundary. So we just deal with this type of system and let you familiar with different type of potential, how we deal with the Schrodinger equation or eigenvalue problem, right? So which, remember the, just remind you. So wave function in this spherical coordinate, we have this function of r theta phi, right? So the only radial part is radial part, and the angle part we already know. That's a spherical harmonic. So like this, and then we can, we know the solution. What we need to do is solve this radial function. So for the r, the radial function we have a radial equation. Now we are going to use the radial equation is this, remember we have a 3 type, right? Now I'm going to use this one. The reason why we use this one, we can apply either the power series method or Kaplan heterogeometry equation, differential equation which you learned, maybe I think you learned from the Dr. Jenkins 517, if I've seen. Okay, so we use this one, if you remember. And what is U? Just remind you. E, but square minus L plus 1 R square minus M square omega square M square plus square U R equal to 0. And here U R is R, lower R multiplied the radial function. So the radial function for the radial wave function for the radial equation for the radial function, we have several either use this one or we introduce U as function R, which is defined by this. So then the radial equation reduce this. Remember this, right? And here this is potential energy here, and this part is the energy moved to this side. This associated with the radial kinetic energy, and this part is if you say the repulsive potential side. So if you remember this, okay, that is the reason why we use this one, not use this partial R and R squared partial R partial lower R, not that one. The one which we use in this problem, we didn't use this one, right? Okay, so now, because there's no boundary, right? No boundary condition, or the boundary condition in this case is different. So we have for example, first, before, when we deal with this type of system, when the potential exists in the whole space, we always examine the behavior of the asymptotic behavior. Either R go to 0 and R go to infinite, since physically require these functions to be finite, right? So we have to examine. Okay. I think the same. Behavior. This is also when we deal with hygiene item. So we know the Coulomb potential also no boundary. The R, effect, the range of the effective potential is from 0 to infinite. So when we deal with this case, we are going to examine the asymptotic behavior, or you can deal with this one is condition, this boundary condition. So that is we have to examine this equation before we go to the details. In that way, we can have the behavior of this. That means we are going to find the limit, and then we find out that these functions be sandwiched by these two asymptotic behavior, right? So now the first one, R go to 0. Let's consider when R go to 0, this equation dominate term, this one, we can ignore because R go to 0, this go to 0, right? And when R go to this one dominate, right? And this is constant, so that means this term and this term will dominate this equation. So in this case, you will see here this equation will reduce to this one minus L plus 1 R squared U R equal to 0, right? Do you agree? That is the idea. That is when we deal with this type of system. We first examine this asymptotic behavior. So the first one, look the equation, which term dominate, and then that means this limit, the wave functions be sandwiched, or the enveloped inside this. So now we want to see the behavior of this. Then what is solution? This type of solution is U R if I say this, do you agree? Okay, so now let's do the second order derivative, right? First order derivative, we have L plus 1 and R to the L's power. Second order is R to this L minus 1, right? And here, you have R minus 2. So you remove the R minus 2, you have that. Okay, just double check. So here, right? So second order is d U square d. Because or partial, let's use partial right there, because it's only function R, so either d or partial is fine. Square is if you use this one is 5 plus 1. L minus 1. So then that equation becomes L plus 1, R to the L minus 1, minus L plus 1, R squared, and then this R Q plus 1. And you can see here, so this is 0, right? Because if you take the R squared in denominator, you have R L plus 1, so this cancels, right? So yes, so that means this gives us the behavioral, asymptotic behavior of this radial function when R goes to 0. So we have, that means this includes this part, this behavior, yes.
Are we saying the 2me over h bar squared is just really small?
Yeah, this is a constant when R goes, so this one,
Goes really big.
yes. So these two ignore.
Okay.
Okay, now how about the second one? R go to infinite. This one can be ignored, right? And this one dominant. This one also can be ignored. So this is partial. It's minus, right? Minus m square over square or h bar square r square. I think I made miss. Yes, there is an m. Okay. R equal to 0. So what is the solution of this? Very simple. If this is plus, that's a sinusoidal function, right? If negative, that exponential will be real, right? So the UR is something like this. If you are okay, let me write down the 2, and then we drop one of them which is not physically acceptable. So the solution is like a exponential. Introduce. Okay, I need to introduce because this is coefficient. So let's introduce this define psi is square root m omega h plus r. So here this is set to the false part, right? Because it's a square here, and then. Here I multiply this, multiply the constant and divided constant, and we have this the same as a partial square u, partial square minus here. I don't think it's a square root. Yes, okay, square root. So that is square. Okay. Okay. So I have because it is a false power, so I divided this one. This became power second. Since I need to divide it here, multiply this cosine square and divide it cosine square. So I have a cosine to the false power, cancel cosine square, right? So that is this one. Then this solution, sorry, no R. So this solution is just this either positive or negative, the exponential function, which is 0 power. Since this is negative, if a positive, we know that is imaginary, then we can make this convert to the sinusoidal function. So the u as a function psi is either positive, let me see, Okay. Negative first. Right, we have either this one or that one. That is, okay. And this one we have a job. Since it's unacceptable. Okay? Since we discussed R go to infinite, that means psi also go to infinite. Then if I go to infinite, this diverge. So this is physically not acceptable. Then when the R goes to infinite, this is the behavior of this U function. So finally, okay, so finally we have U, this radial function should be intermediate between the R go to these two limits, 0 and infinite. Now I'm going to see if I index here. Even do not use index is fine. Do not use index. So R, and then R then controlled or enabled by this function which is R go to 0, so this must be dominant. If this is a function, finite function between 0 and infinite. And then they will go to R, go to infinite, be dominated by this, right? Minus, so I have set squared half, right? Half is m omega h bar 2 h bar and r squared. Okay. So this one control the 0 case. R go to 0, this control R go to infinite, so this be a kind of finite function required, right? If it's diverse or go to infinite, then we have to make a modification or make a sum of adjustment, so to make sure that this be finite. Like this. So that is we are going to do. We do not know, but at least we know that this function to be like this formula, like this kind of behavior, and then the unknown function fr is we are going to do. So how to do that for fr? Since we know u satisfy this differential equation, then we are going to substitute this u in this formula to here by do this second order derivative, and this is a zeroth order. That is just the original, and then try to find function for f, right? So that is our next job. That is for most cases when we deal with if the potential is defined in the whole space. Limit, two limits, and then we are going to have this behavior of the function and substitute into the differential equation to try to do this. Okay, so now let's look at this one. First order, since we are going to find the second order, right? So let's do the first order. Partial u, partial r. So now we have three terms, right? So we do one by one. If we do first partial f r, partial r, and keep these two terms same. Then second one keep f r, but to this one. So this one's at l plus 1, and r to the l's power, because l plus 1 and minus 1, that's l power. And f r and exponential. The third term it is negative. Now we are going to do this, right? This one we have a negative with constant r is 2r, right? 2 cancel, so we have a minus m omega h bar, and we have r, right? So now let me keep f r first. R, we have this r l plus 1, and plus another r, so the l plus 2. Okay, a little bit longer, so now let's take some same factor outside. So we have inside partial f r, and keep this, the exponential term take outside, right? And plus l plus 1, l and r, and minus m omega h bar f r to L plus 2. And outside is exponential. This is the first order. Then we are going to do the second order, since we need this one. So we have the inside parentheses and the outside we multiply the constant, the exponential. So let's do first inside. Inside is the second order, right? Partial square, partial f partial r square. Keep this one r l plus 1. And then do this, so we have l plus 1 r to the l partial f partial r. Then we go to this one. So this one, let's first do this partial f r partial r. So we keep l plus 1 r l. And then the second one is l plus 1 r l minus 1 f r, right? This term. Then we go to this term. It's longer, so now here, this term is minus m omega h bar partial f r partial r, and keep r l plus 2 and the minus l plus 2 m omega h bar r l plus 1 f r. So that is an explanation.
While you're kind of stopped, I'm sorry, I know
Yeah.
my brain's running really far behind where you're at
Yeah,
right
we
now.
got-
With the equation that you have.
Yeah, this
And
one.
we looked at our first case where we did r minus 0. R approaches 0.
Approach, yes.
I'm okay with I understand the math of
Okay.
dropping the 2me over h bar squared term,
Uh-huh.
but
This
physically,
one.
right, because basically what we're saying at that point is that r squared is much, much less than h bar squared. But is that,
No, this one, when r go to 0, this term is 0.
yeah, but your first term,
The first term is constant.
right?
Right. So, yes, you say why
But
not?
aren't you way below wouldn't your r be way below the Planck scale at that point before you, so that's, I guess
Yeah.
is it physically meaningful?
Physically meaningful, because we know this is a constant energy, right? That is for, if this is come from this, if you remember this, let's do this. These terms come from here, move to the left side, right? And this one are come from here. This one is potential part. So potential, then you can, potential, okay, when r go to 0 is ignore. That you agree, right? This is the r function, this is really r. So that we consider here. And this is a constant. This just, it is, you can, physically you may say, okay, maybe when this, this term, we know that this is repulsive potential energy. If centrifugal potential, something like this. So that will diverge, something like this. Remember, in the theoretical mechanics, we have a potential. So this is a term something like actually something like this, right? There are some other constant here and r, and this is the potential. Of course, that is we consider the Coulomb potential or something like this. And then we have effective. So this one, when r go to 0, this is a dominate. Is here, and this is a okay. This is a now in this case is not this one. In this case is this one, right? Real potential here. So the effective, just I do not discuss effective potential, but here, so then go to 0. This one potential contributed ignore, but this one is diverged. Then that is constant something here, energy here, right? So that means that is for if you consider certain r, maybe you need to include that term. But where r is so close, so this this effect is still much, much smaller than this, the repulsive, this potential here. So then we say, okay, around this area, they dominate this term. Just if you say physically, that is a dominant. So we are going to see if in this dominant area, what behavior of the wave function looks like. Because this is a constant, right? That is correspond to this one. So this does not depend on R. So we're looking for if the particle is very close here, and you will see we have 3 contributions here, and this 3 contributions, which one dominate? I'm not sure that makes sense.
Yeah, I mean, I just need to turn it over in my head, I guess.
Yeah, that then we will go to infinite again, go to infinite, this term go to infinite.
Right.
And this term go to, so we can ignore this effect. And even though this is constant, but this term is much, much larger. Well,
I guess the way my thought process is working on it is, in a quantum realm, we would never be able to measure an R that much smaller than the Planck length to be able to do anything with it to justify dropping that term.
okay, you just say if a quantized, that is, you're talking about this one? How the measurement of this, the fluctuation?
Yeah, because, what, Planck length's like 10 to the negative 35?
Oh.
Right, and you've got an h bar squared comparing it to an r squared, so your r would have to be much smaller than that.
Smaller than this, okay. 10 to the minus 35. This small?
Yeah, but your r would have to be much smaller than
Smaller than
that
that.
for that term to become significantly larger, right?
You,
And that's where I'm kind of getting lost on what the physical meaning of that
okay,
r
you
is. Am I
consider
making
because
sense, or
this
am I
one
just
is
losing
small,
my
right?
mind?
That one is small, so you consider this still, even though R goes small, or when R goes small this range, then this term can be good drop, otherwise you cannot drop. This is what you say, right?
Yeah,
Okay, the mass also 10 to the minus 13, so this is a 10 to the, so there's a cancel. And the energy is yeah, well, I mean, this is, we probably have to say that is mathematically.
okay.
Just try to find the wave function behavior, do not divert. Do not make the function solution is not finite. That we will to avoid that one mathematically. And this is the give us the like criteria or the range which how small it can reach. Right? That is what you value. Yeah, I think, good question. Let me think about how to reply this one. If not, at least mathematically, let's be control this wave function itself, the solutions be finite. So that is, we need make this factor to characterize the finite when R go to small. Any other question? If not, yeah, you have.
The only difference, if you include that term, it would make it like a non-homogeneous differential equation. So you would still
Yeah,
just be
you
adding
just
some,
like here you have a constant instead of. right.
still just be adding some.
Yeah, constant and then like shift,
Yeah.
like R maybe go to R minus R naught something, right? Something like this, maybe something. Because you can move that term, you can define the new R prime like this, and then you modify things partial U, partial U, partial R prime is partial U, partial R, right? Because it is constant. So the equation will not affect by you include that constant. That makes sense? if, so far still mathematically, but if we consider that one still physically, how small it is, suppose we can, if we can reach that one. Okay, we haven't finished, so now this is a first, do the second duty for this part, but not this one, so then the remaining part I'm going to use the parentheses, which is this, which I will not read, right? Again, then do, and then we have a factor, this is a minus h bar m omega r exponential minus m omega 2h r squared. So, lot of term, right? So now, what we need to do is put those terms here, and this one, there's no derivative, and then this, we are going to replace this one by that. Then we are going to see some term we can cancel, and some term we combine together. Now, to save time, that's just carefully do it, and then I'm finally give you this I think okay, let me just substitute, let me just say substitute here, and finally this equation reduced to function of f. Second order plus 2 multiply L plus 1 R minus M omega h bar R partial F R the first order, and space here, plus 2 M E h bar square 2 L plus 3 M omega h bar F R equal to 0. So now this is only second order partial derivative plus this zeroth order. Now we have a second order, first order, and zeroth order for F. So now we are working on this. Even though it looks complicated, but now it's doable. Or whatever is, we are focused on this, we are going to solve this since we already know the two asymptotic behavior. So now we're working on this. So we have a two method to solve this. Okay, and textbook only take this power series. I'm going to also include this confident hypergeometric method. This you already know, right? Okay, very good. That's why I want to, you learn from the mathematical physics, now we try to apply the system. And so I think when I deal with this one, I just maybe speak a little bit quick. This one, I think when you in the undergrad, some of you learn this quantum mechanics from 500 level. This is the most case for the undergrad student to learn this method, this way. Because this one is also very easier to solve. So now let's just try to remind you how we use these two type of method to deal with this differential equation, special differential equation. And since you already learned this confident hypergeometric method, that really depends on condition will reduce to different type of case, right? So this is one of the case. Now let's first use the power series method. So for so-called power series method means we do not solution, but we know the solution can be expanded in terms of power of variables, right? So now let's say in terms of, I'm going to this infinite series, right? And whether it is infinite or finite, we are going to discuss since we require the function to be finite. Coefficient AK and R to the kth power. So this is unknown. So in the power series method, we know the formula can be written in terms of power series, but then the next job is try to solve this coefficient. So that is a step by step. So initially with U, right? Then we reduce to the differential equation for the F. Then when we introduce X to be in terms of power, then we focus on K, on AK, the coefficient. Okay, since here we have, I think I can use this part. So here we have a first order, second order. We need to do this and substitute into that differential equation. Since power series, it is very easy, right? So the first order, df dr is very simple. It's k a k r k minus 1, right? And second one, second derivative is keep continuing, right? K minus 1 a k r k minus 2. Okay, and then we are going to substitute this into that formula. So because, right? So now let's do that. The first one is second order, right? So k from 0 to the infinite, k minus 1 a k r k minus 2. Very simple. The second one is the coefficient 2 L plus 1 r, right? So r minus 1 over r, right? Yeah. R minus m omega h bar r. And the first order is this one, right? So that is summation k from 0 to infinite k a k r k minus 1. Then the zeroth order. So zeroth order, just put here plus minus plus, right? 2me over h bar squared minus minus 2l plus 3, right? Yes, 2l plus 3. And m omega over h bar. And then the summation k from 0 to infinite a k r k to the k's power equal to 0. So since these are all three the series, then we can combine together. I'm going to make it all together. K from 0 to the infinite. So here, I take the AK outside and take this R to the k's power outside. So the inside is, first one is a K minus 1. And here we have R to the minus 2, right? Since I take RK to the outside, so we have a minus 2. That's the first term. And the second one, plus okay. Now, second one is interesting here. We have, actually, there's another term. So you can see here, this is R, right? This is a K, RK minus 1. So that if this term is RK minus 2, right? So that should be same order with this one. Then the coefficient should be here. So I have this one and plus there's a K. There's a K also. There's a K here. So this is k multiply L plus 1, 2L plus 1. Here I have 2k L plus 1. So this one to the minus 2 power. And the second one is this one. This one here, this is k minus 1, so that is k. So this term is same as this one, so we put together. Is, we put this one as a first. Here we have a k, right? So here is a constant. Okay, this constant for 2m or h bar 2 first, then minus here. 2L, I have this one, I have also this same constant here, but there's a k. There's a factor 2, right? 2k, 2L, but minus L and 3, right? So this together is 2L plus 2k plus 3 m omega or h. Okay, then outside is AK RK equal to 0. This is minus, this is minus, all are minus, right? So then you can see this one is, I take this K arbitrary, right? So if we want to have those term, okay, since we have another term, so in principle, it will written in when K equal to 0, then only this term, this is inverse, right? The second term. Then when K equal to 1, we have this K equal to 1 and multiply this as minus 1. And the remaining is positive, right? So in principle like this, we have sum of coefficient here, minus 2 plus sum of term minus 1 plus sum of term R0 and plus sum term R1 and go down. So if we reorganize this series like this, and if that's equal to 0, so if that means, okay, that requires each coefficient, right? Those should be 0 each. Right? That is, yes.
Where did the r minus 1 term go?
R minus 1 term is here. When this k equal to 0 is this term. But when k equal to 1, you see I have a second parenthesis, so that this k, rk.
I'm saying with the k minus 1, r to the power of k minus 1?
No. K only is from 0 to 0, 1, 2.
Right.
So let's consider k equal to 0.
Yeah.
This term is constant, right? This term only ak, or a naught. But this one is r minus 2.
Okay.
Then the k equal to 1. Here is a1, r. And here we have r minus, so that is r minus 1.
Okay.
And then remaining is higher, right? So that is this come from. Okay, so that is required this. Then from here we can define this coefficient. Here we define or determine. This is the equation to determine the coefficient. But for the first two is the coefficient is not regular, but when the k larger than 2, we can have the formula. So now let's consider first case. First, k equal to 0. So k equal to 0 case corresponds to this minus 2 term, right? So k equal to 0, so we are going to find a naught equal to how much? Then we are going to see here, that means ask us k. I already, if I take this, I can take this k outside. So this is a k, this is 2L and 2, right? So this is minus, so that actually that is k, 2k plus 2L plus 1, a naught equal to 0. You see here? I take the k, all the k outside, so then I have a k minus 1. We have 2L plus 2, so minus 1 plus 1. So this is 0, but this is a 0, right? So because k equal to 0, so A naught is arbitrary. Since 0 multiply anything can be 0, then in this equation, but we do not know how much A naught is. It's be no any restriction on A naught. It's be arbitrary, non-zero, or maybe 0. They depend. So we have this first conclusion is this one from this R minus term. Now second, we consider k equal to 1 case. We are going to see how about A1. So that is R minus 1 term. Now again, R minus 1 term still from here. This one will not contribute any R1 term, right? The R minus 1. So again, that means k plus 2L plus 1, A1 should be equal to 0. So k equal to 1, right? So that is 1. 1 multiply 1 plus 2L plus 1, A1 equal to 0. Then we know these are not 0 because L from 0, 1, 2, right? Whatever higher. So even L equal to 0, this is not 0, right? This is 2. 1 multiply 2 multiply A1. So immediately have A1 always 0. That is interesting. So later you will see all the odd coefficients be 0. Now we go to for k, the third one, right? Third, now we can have the recurrence method. Since all the coefficients, we have a formula for k larger equal to 2. In this case, let's go back to see this equation here. Now, I rewrite. Let me rewrite here. So here, when k equal 2, this is A2. But that is the k equal 2 is the 0th term, right? Because 2 divided by this R minus 2. So that is 0th term, constant. And then, but when the k equal 2, this one is not constant. However, when I discuss k equal to now to 0, there's a constant term. I didn't count, since I just count this one. So that coefficients we go to the k equal 2 with that k equal 2 with that term and k equal to 0 with this term. Then you will see here, that be like this. Okay, the coefficient is, I'm going to rewrite here. So k, now if I still use k from 0, then here the coefficient k plus 2, L plus 1, here. I will explain what happened. So now k plus 2 and k plus 2 plus 2L plus 1. Now the coefficient A is k plus 2 term. That is this one. So then if I rewrite that, or you can say k prime from 0 is equal to, this case k equal to 2. So then the k, you replace k prime equal to k plus 2, right? So here is k plus 2, and the coefficient corresponds to k plus 2. That is the 0th, this constant term, which corresponds to, in this term, is k equal to 0. Plus, so I didn't change that one. 2mE or h bar squared minus 2L plus 2k plus 3n omega h bar ak. K equal to 0. Now in this case, k from 0, so we have constant this term. But this corresponds to the k plus 2 term. That makes sense? So that is here, you see I replace k by k plus 2. So now you can see, in this case, whatever k from 0, 1, they all follow the same formula, the coefficient same. So that means we have k plus 2. This one Now here, k plus 2l plus 3. ak plus 2 plus or equal to, okay, let me see. I use minus. Okay. That's just plus 2m e h bar square minus e2l plus 2k plus 3m omega h bar. K equal to 0. For any k, if I ask for any power of k from 0 to infinity, if this equal to 0, so coefficients be 0, then that coefficient is for given k, the first term be k plus 2 coefficient, and this second term is ak. This term add together should be equal to 0. Then we immediately found the relation between a k plus 2 and ak. So ak plus 2 is, I divided this to the left hand side, right? So that is denominator k plus 2, k plus 2l plus 3, ak, right? And then that one we move to the right hand side, it's the next sign, so this is the first, 2l plus 2k plus 3, m omega h, h bar, and minus 2m e over h bar. Now we find the relation of coefficient between ak and kk plus 2. So this is a recurrence formula. You familiar with this? Okay. Yeah, that is any case if you use a power series method, you always deal with your differential equation become a power series equation, and then you are going to deal with the set up the equation for the coefficient. That coefficient gives us the recurrence formula. Okay. So now let's summarize. With that, so if, let's consider example, if this k equal to 0, so we have a k 0 plus 2 is a2, right? So now if we know a naught, we can find a2 from that equation. That is 2l plus k is 0, right? 2 multiplied and plus 3 m omega h bar minus 2m e or h bar square a naught, and denominator is k is 0 plus 2, and then another is k plus 2l plus 3. So this one is 2l plus 3, and that is 2l plus 3 m omega h bar minus 2m e h bar. So very easily, if we know a naught, we can find a2. And how about the next one? If k equal to 2, you may say why not 1? I'm going to for the R numbers. So that is 2 plus 2 is a4, right? a4. So if I know a2, right? So now I go to here. 2l plus 2 multiply 2 plus 3 m omega h bar minus 2 m e h bar squared. This is a2. And denominator 2 plus 2, 2 plus 2l plus 3. So you have 4, 2l plus 2 plus 5. And that is 2l plus 7 m omega over h bar minus 2 m e h bar squared a2. So if we know a2, and yes, if we know a naught, we can obtain a2. Then we can also obtain a4. So continue all the even number, right? We can obtain. But only need one, a naught enough. Then how about A1, A3, A5? A1's here, 0. So all others be 0, right? Okay, so now you can see for k equal to 1, then we have A1 plus 2 is A3. So that is some constant, that formula A1, right? That's be equal to 0, since A1 is 0. Then you can do the same thing, all the odd number equal to 0. Okay, now finally we have the formula for the coefficient. So finally you can have this function. We can have write down the function as, so now this is our goal, right? Fr is function we have say, k from 0 to the infinite, and ak are k, right? That is our initial. And our ak, k, a naught, a1. So now is reduce k, only take even number, 0, 2, 4, or even number of ak are k. So from here to here, we use this result, right? Okay, now we had formula, and now I'm going to get the index here. Okay, now still, I keep in mind, at least it's function L, right? Remember we have the function, the different equation here. For given L, we have given solution, right? So the function here actually already has index L, but I'm going to, there's another index, and put together when we discuss this. So I'm going to put together. Keep in mind here, there's some of the index which is given by the quantum number, right? So now we have this. Now if I have this, let's consider the exam, right? So exam, if the asymptotic behavior, because we want to have the finite, but may not. Mathematically we have this, but may not physically accept. So when R go to infinity, so you can see here, this one is k over even, right? So that is, if you agree, that is go to this power. Since this is when, if you use k prime, that is 2k prime, and k prime from 1, 0, 1, 2, 3, right? So that is this one, right? You know this. Okay, because, so this is infinite, right? Or diverse. So we have to truncate. We cannot make this, because the question is here, is this one. If finite, it will not go to behave like this. This is an infinite power theory, then we know that is go to this exponential function. So we have to truncate. Truncate is summation k from 0 to infinite to k from 0 to some k maximum. Become a polynomial or finite series, not infinite. So that is the goal. Okay. All right, so now we are going to find what is k maximum. So that means here the final solution, the physically accept solution to be k from 0, all the even number, and to the k max, and ak are k. So this is a formula here. So then how to find k max? The k max means this is this if, right? If the coefficient a k max plus 2 equal to 0. So here it is here. So suppose we have a k max which is non-zero, right? That is, means the summation to here. Then if we want to truncate, means all term after the k max be 0. How to control that coefficient? So that means ask, right? Then we can have this. we can reach this one, right? So now, that means we are going to look at the coefficient with Kmax plus 2. The reason plus 2 because they have always this relation, right? So, now we have the equation here. Use this space. You need this equation. So that means K max plus 2 equal to here, right? 2L plus 2K max plus 3 m omega h bar minus 2 m e h bar square over K max plus 2 K max plus 2L plus 3 A K max to be equal to 0. That is A K max plus 2. And equal to 0, we know this is non-zero, right? This one is non-zero term. Then if asked this, that means the denominator should be 0, right? So that means 2L plus 2K max plus 3 m omega over h bar minus 2 m e h bar square equal to 0. Okay, now this gives us a lot of energy because this equation, what is the unknown? This is the unknown, right? So for this case, we want to determine from this equation, it is not only the give Kmax, but also give the energy. So from here we found energy, this one gives us energy by just move this to the left-hand side and multiply this constant. So energy finally is h bar omega L plus K max plus 3 over 2. Very simple. And you almost look familiar with this. Ignore this term, but you know this term, right? This is a zero point energy and h bar omega, like a phonon. So because we know the vibration is phonon, right? Or photon, that's something like this. So now, these two numbers, but we know L from 0 to 1 to all. So now from here we can define the Kmax, right? So now, here, first, Kmax, we do not know, but at least the Kmax can be 0, all the possible numbers, right? But even. Okay, and but L is 0, 1, 2. So L plus Kmax is another quantum number. Since Kmax is independent of L, so that quantum number should be also independent of L. So we have now, let's summarize. Define the 2n equal to Kmax, because Kmax is even, right? So n can be 0, 1, 2, all the numbers. And n, lower n is Kmax plus L. Then the lower n from this one is also possible. So now the Kmax is depend on what, so how much we can expand in this power series. Later we are going to discuss, you will see for given n, we will have a given Kmax. So now we introduce a new quantum number here. This is nothing but the addition of these two L plus Kmax. And then you can see here, since Kmax is an even number, so I introduce capital N, but this one, the purpose is just to make this an even number. Then since Kmax from 0 to 4, then the n should be, capital N should be 0, 1, 2. So now you can see here, this one, if Kmax equal to 0, L can be 0, so that's the smallest one is 0, right? And then Kmax may be 0 or this 1, or this 0, this 1, so that the first one is 1. So the energy is h bar omega m plus 3/2. Independent of L, because whatever it is, they together give us another quantum number. Then I'm going to give a index here. So that is allowed energy or eigenvalue of energy, or eigenvalues, right, of the solution. So we have a wave function, we also get the solution of energy. Now you can see the picture here. I'm going to give you a table series. So now if it's n, see energy only depends on lower n, so En, but the n, if you want to have this depend on equal to k max L, right? So when n equal to 0, then that is h bar omega 3.5. Here, this be also 0, right? And states, I jumped, okay. Finally, remember here we have this R theta phi, which is R, L, M, right? Remember at the beginning of the function. Now we have R. Okay. Let me skip this one. Wait. So I will not do here to discuss the degeneracy here. But you know M. So give me L since, okay, just remind you, and then later I'm going to discuss this one. Is R, this one, LM, right? So that definitely have LM. Now R is NL. Since here, the radial function N and L, right? So that's this radial function, you see here, as I said, this one's be given L, we have a solution. Now we have another quantum number. So that is something like this. Later I'm going to discuss these details. But I'm going to see is the degeneracy of a given n. So here, when L equal to 0, M equal to 0, so this one only 1, and this one only 1, N is 0, L is 0. So we have only one degeneracy states, right? Second one, when N equal to 1, lower case, lower N equal to 1. So we have 5. Then here it is possible, there are two cases, 0, 1. Then we have 0 plus minus 1. 1, 0, and this comes is M is 0, right? So you have how many states? 4, right? I think, okay. When that is N and L is only 1. L equals 0 and 1. I think there's a 4 states. We have N equal to 1, L 0, 0, and N equal to 1, 1 plus minus. So if this is 2 here, this h bar omega 7/2. Then here, wait a moment. Sorry. Capital N, yes, capital N can be this one. So now L N, if N takes 1, then L N takes 1. Okay, now come here. N takes 1, K max is 2. So this be 0, right? I think N takes 1. N takes 1. N cannot take 1. Yes, that is my mistake. Here, that is to be careful. Since it's an even number. So when this lower N equal to 1, K is be 0. K equal 2, this will go to 2, right? So this be always 0, this is always 1, so we have 3. 0 plus minus 1. Right? But now come to here. N equal to 2. 1 is, this one equal to 1, so we have 2, this equal to 0, so we have this. Another, if this is 0, then this be 2. No 1, right? So you have these states, you have M, you have 0, and this one you have 0 plus minus 1 plus minus 2. So we have 6. And the formula. Here, the degeneracy of forgiving n, so now this end, I just do not derive the details since the textbook gave you this example here. But did you see this example? Let's see here. Example of 6.2, page 6.2 and page 350. Okay, discuss how to obtain. So here, I just gave you this, either you select the L, take the even number, like from here, even number, or odd number. Okay, to n, for given n, so that is 2L plus 1 for m, right? For given L, we have 2L plus 1. That gave us this number is half n plus 1 and n plus 2. For odd number, same thing, L from 1, 3, 5, given n. And you derive that example already shows the same thing. Very simple, this summation or series. Okay, it's time now. So we discussed the, you can, I just want to give you the ideas. If we use the power series, the power series, when we deal with this function here, we will come back to deal with the coefficient. Then with the coefficient by the physical required, the finite function, so we have a truncation. From truncation, we can determine allowed energy here. Then we will have, come back here, so now I'm going to say that is NBL. Then finally here, we are going to discuss the function or eigenstates. The behavior eigenstates and how to determine it. In your homework or some case, you need to play with that. For giving n, what is the ground state, first excited states, how to determine this, in particular, how to determine the coefficient for giving n, since the truncation Kmax, right? Kmax n and the relation between n and Kmax is this one. Okay, we can discuss this one Wednesday. Then we discuss the second method. Second method, if you're familiar, then that is easier. Once we know the solution, we again discuss this physical required the function. By that condition, we can determine the allowed energy and the function. Okay, the homework, some of you since has a qualified exam, you can turn after qualified exam. For you either same with them, or if you think I can finish earlier, then you can.
I have a question about the third problem on the homework.
Okay, you will work on the third one, okay.
No, I was just looking at it, trying to see like the starting point.
Yeah,
So that's from this J function right here.
yeah.
So that's what
Deep
you
one.
say the boundary condition for the unbounded
bounded state,
states.
that is the energy logic state, right? The energy positive case, yes. So we have the boundary condition equation.
This is for region 1
Yes.
equal to region 2.
Yes.
It has to satisfy that condition.
Yes.
Where J1 is equal to
This is a J1 front,
she did
this is
it.
the definition.
Yeah.
So you need a variables to K, I,
submit
R, not
time,
R.
then you can submit, otherwise you can submit next month.
And this one is definition.
I mean this.
This
Yeah,
is
electromagnetics
second
we have
region,
25.
right? Yeah.
Yes, same. So,
Also,
does he
you
also?
just substitute.
No, we have not talked with
And
him.
set up equal to 2. So that is, when you set up equal to 2, you find this like a transcendental equation.
Did you see my little email
Yeah.
Okay.
for Dr. Kilkoff? Do you want to grade this thing, or do you
So
want
for
to cycle through maybe?
L equals
I'm not
2,
good with you.
I remember
Oh,
you
for
saying
L equal to 1.
Oh,
Sorry,
because we're
L
going
equal
with
to more
Zing
complicated.
and Neil.
Here,
They
find
have
this
other
equation of
Okay,
this
you
one.
have
The
the
L
other
equals
one.
0, I already described it, right?
Discuss it.
So,
The L
you
equals
to,
1.
to follow the
in
same
this
thing,
week,
and just use to 1.
This week,
You
Yeah,
have
no,
to
I'll
use
do
it.
from-
do
Right.
your,
Yeah.
your,
Oh,
your
yeah.
value
Okay.
and my Batman, and after that, we can alternate. The 2 days, two homework is graded, your practice 7, we have already graded
I'll
one.
probably give
one homework.
problem number
Yeah.
3
And,
an attempt before
after
Wednesday,
that, if
so
you
that
grade-
way I
if
can
you
come with
grade
a
your
more
part
solid
this week,
question.
and I will grade my task, and after
Yes,
this
okay.
Thank you.
Oh, yeah, yeah,
one,
yeah.
then then we have,
Yeah,
Dr. Yu,
Yes.
I think he's
Yeah,
still
yeah.
not being.
Oh,
I
sorry.
think they have,
That's what I'm saying.
10 assignments, 10 works,
Yeah.
and one, we just finished one, and 9 is left, and so to alternate.
I'm going to the Cardinal
Check your email
Cover.
though. That's it.
Yeah.
Oh, are you?
Okay.
Yeah, I'm gonna try and start doing like a regular thing to where this just basically I want to get some produce, bring to the cardinal cover, and then